All right, so we're coming to another highlight of this workshop, at least to my impression, which we scheduled towards the end because it gives us an outlook into the future with modeling of climatic conditions in Europe. And for this talk, I would like to introduce the speaker, Dr. Juliane El Zohbi. She is scientist at the GERX, the Climate Service Center Germany, of the Helmholtz-Zentrum Hereon in Hamburg. And she is one of the initiators of the Adapter project that develops and provides regional climatic models for Europe. And Juliane, we are keen to hear your talk and get an explanation what kind of modeling and to which regional size it will be possible and what these models will tell us about our future weather conditions. Juliane, the floor is yours and please go ahead.
Thank you. Thank you for the invitation. And what we're going to do now for the next half an hour or so is that we're going to leave the plants, we're going to leave the soil and the ground, and we will take off to the atmosphere, and we will be dealing with the climate for the next 30 minutes. And I guess why I'm invited here and talking about this topic is because I'm working at GERX, as Thomas Altmann was saying. And our daily business is that we are dealing with climate modeling data and trying to make sense out of it. And we are not doing that on our own, but together with users and practitioners from outside of the scientific climate bubble world, and do a co-creation process to make sense in a way out of the data that it's usable and useful for the purposes. And why we're doing it, it's to support then decision makers on the way to adapting to climate change. Okay, but when we take a look back to the past, I'm showing here this curve or those curves, and what they are representing is the global mean temperature difference from 1850 until today. And when you have a look at it, I mean, it's so obvious that the temperatures are rising, especially for the last few decades. And I'm also pretty sure that I'm not saying any news to you about that. But what is striking is that we have almost already reached 1.5 degrees above pre-industrial levels by today. Okay, this is the past, that's what we know, that's what we have experienced, but what is more interesting is actually what do we have to expect from the future? How will the climate evolve? And how do we gain knowledge about that? For that, we use climate models. And before I come to the results and the output of the climate models, I want to do a little detour and present to you what climate models actually are. So what you see here is an illustration of an idealized climate model. And this concept shows you that the basic concept of a climate model is that we take the globe and it's surrounded by three-dimensional grid cells that can be presented by mathematical equations. And that describe the materials in it and the way energy moves through it. And the advanced questions are then based on fundamental physical laws like fluid motion and chemistry. And to run a climate model is so that we scientists specify we call it climate forcing. So that means, for example, how much greenhouse gases are in the atmosphere. So that is prescribed, and then the climate model does the calculation. And it's so that really for each cell, those equations are calculated and then passed to the next neighboring cell, and the equations are solved again. And as you can imagine, this is pretty computational intensive. That's the reason why we're using such huge computers, such supercomputers. And as this morning, often there was also already mentioned that we're dealing with a lot of data. And from the climate modeling community, I can tell you we have huge type of data. I mean, it's like, and it's also increasing. Like a couple of years ago, we were dealing with terabytes, and now we have petabytes of data we have to store somewhere. And what I want to show you here with this illustration is that often when people hear climate models or Earth system models, they think of the atmosphere. and think of the sky and the clouds. But not only this, is also that the climate models have one component that is dealing with the ocean and the processes that are going on in the ocean, and of course also the vegetation. So there's also a vegetation model in there, and then there are also the feedbacks between those compartments. They are also modeled. So these are really huge complex models when we talk about climate models. And this question was already raised. Okay, with what resolution are we dealing with? I mean, as you can imagine, the globe is big. We have a lot of those 3D grid cells. And I want to show you this figure here. So when we look at this one with FAR, that stands for First Assessment Report. So that is the first assessment report, IPCC report that was released. And back then we were dealing with the resolution of those grid cells by 500 to 500 kilometers. And by now, this figure is here for AR4, and now even the AR6 was released. And we have now a resolution that is much higher, and is by about 100 kilometers for each grid cell. I mean, that may still sound very coarse, but from the climate modeling perspective, that is a huge step in terms of a higher resolution. Okay, as I was saying before, those climate models, to run a climate model, you need to prescribe some boundary conditions. And one of those boundary conditions is how much greenhouse gases are there in the atmosphere. And I mean, as we don't know how we will behave, the politics, economic, and so on, the only help we have is that we use scenarios, or as it's called, representative concentration pathways. And when you look at the bluish color, behind this one here is then the assumption that there will be a lot of climate mitigation and the greenhouse gases will reduce. And the opposite to that is like the reddish color, so the top curves, and there's the assumption behind that we do nothing, no climate mitigation, business as usual, and there's a lot of there are a lot of emissions of greenhouse gases into the atmosphere. And that's what we use and put them into these climate models and let them run. And what you see here is the calculation of the global mean temperature. And again, in blue, this is then presenting those scenarios where we see a lot of climate mitigation is going on and a reduction of the greenhouse gas emissions into the atmosphere. And what you see as a result is that the temperature stabilizes. I mean, it still increases, but it stabilizes. And the opposite is when you look at the reddish color, that is where we say business as usual and no climate mitigation. And we see a strong increase in temperature. And the message I also want to convey here is that when we talk about climate projections and future climate change, it's that we're all dealing with a bandwidth. We always will have a spread and not just one single number, because that wouldn't be serious science, because we simply don't know how the future will evolve, but we will always have been dealing with a certain spread. Okay, this is just a quick look at one of the products we have developed at GERX, because of course there's this huge amount of data, this huge amount of information, and how to make sense out of it. And this is just an example where the KfW bank approached us and was saying, okay, our employees that are dealing with climate modeling data, they quickly need to access the most important information. So we developed this global climate signal map. And what you see here is the dots with the colors in yellowish and reddish. So they show you a robust increase in very wet days per year. And behind this, there's a lot of significance and robustness testing. So you can assume this is a robust information you get. And with the white and grayish color, those are regions where the information from the climate models is not as robust as for the other ones. This is just as an example. And this is the global view. As I assume that is also true for you, you are more interested in the more regional and local scale. And the solution for that is to take the global climate models and use them as a forcing and to cut out a region, so to say, your region of interest, and run a regional climate model. And those regional climate models have then a higher resolution than the global ones. And when we say higher, it's between 50 kilometers and 2.5. And the climate modelers, or also the regional climate modelers, are not doing it on their own, because I mean, if you have just one model and you have one simulation, it's just one possible evolution of the climate, but it's not really a robust result. So the regional climate models are organized in regional groups, so to say, and the squares you see here on the map, those are the different initiatives where regional climate models work together and analyze and do climate regional modeling for certain areas. And the whole initiative is called WCRP CORDEX. And the results I want to show you and present here today is for Europe, that is the Euro CORDEX initiative. And it's so that here about 30 modeling groups in Europe work together. They meet once per year and exchange, of course, during the year. And what they do is that they set up like a model simulation matrix. That means that when they set up the new simulations, that they decide on how they want to do that. And the advantage is then that the results are comparable and we can derive then robust simulation, that's also robust results from the simulations. And so far, for the latest efforts, it's so that we are having like 85 simulations for the analysis. And the results I'm going to show you will be based on those 85 simulations. Okay, then let's have a look. What do the climate models and those 85 simulations tell us? What I'm showing you here first is the projected temperature change for the end of the century, and under the assumption of the scenario that we see there are a lot of emissions in the atmosphere, there's almost no climate mitigation going on. And when you look at this picture in the middle, you see that there's everywhere there's some color, some yellowish reddish color, and that shows that there is an increase expected everywhere, no decrease and an increase. And what I also want you to look at is at the smaller figures, because they're showing the percentile, the 20th and the 80th percentile. As I was saying, we are always dealing with a spread. And when you look at those patterns, they look pretty similar to the one in the middle. And that means that the bandwidth is not very large. So we have a very robust signal when we're looking at the median. And what does it mean, increasing temperature? It also means that we have to deal with a higher evapotranspiration. That is also important when you think of plants, to keep that in mind. Okay, as I was already mentioning, evapotranspiration, it's not only the temperature, but of course also the precipitation that is important for plants, that they can grow. And again, it's the same analysis like end of the century and the assumption business as usual, there's no climate mitigation. And when you look here in the middle, it's like that you get a completely different pattern compared to temperature. What we see here is that in the northern part of Germany, we see an increase in temperature, that's the annual mean, and a decrease for the Mediterranean region. And when you look at the percentiles, you see that the patterns are a bit different. And that means that there's a larger spread in what the climate models simulate. And that is very typical. It's like for the temperature, we get rather robust results. Precipitation is not as easy in the simulations as temperature. And let's have a look at a combined climate index. So when we have a look now at this one, it's the days where there's dry soil in combination with high temperatures. And it's here the unit is how often does it occur. And when we look at the figure here, and I leave out now the percentiles because that is now easier to convey the messages here. It's so that in the Mediterranean region, you see that dry, hot days become much more common than they are today. And of course, when you have that in mind, that low soil moisture and heat, they amplify each other. So that's also the reason why there's such a strong increase as we see it here. Okay, so this was just in general, and as we are talking about plants in this workshop here, I chose the example of sugar beet to just have a bit closer look what those temperature changes mean for sugar beet, for example. And with that, let's turn to winter and to the climate indicator days with temperature below 5 degrees. So some cooling during winter. And what you see here is that we can expect, from the simulations, a decrease, especially in Southern Europe over land. And that may mean that crops like sugar beet, for example, that require vernalisation might be in trouble. And again, precipitation, because of course it's not only temperature that is interesting. You see here the temperature change for precipitation on the left-hand side. And there we see that there is a tendency of increase in France. But when we look further south to the Mediterranean region, we may expect a decrease in precipitation. And it gets even more obvious when we look at soil moisture, so that then even France and Spain, that we expect here also a decrease in soil moisture, and even during winter. And that is a bit worrying, because often we expect that during winter that there's some precipitation and the soils can recover, but it doesn't seem to be the case. I mean, for this scenario, no climate mitigation and end of the century. Let's turn to July, to the harvesting time of sugar beet. Those are the climate index for dry days. Dry days means for us, it's like less than 1 millimeter precipitation per day. And when we look here at the figures on the left-hand side with the reddish color, we see an increase in number of dry days, especially in Western Europe and France. And again, when we look at precipitation on the right-hand side, I mean, here it seems like there's no increase in France or Italy, but the reason for that is because there's already so little rain that there is also we can't expect no decrease, because if there is none, it cannot decrease further. Okay, so this was like having a look at the analysis of the climate simulations as such. But what I want to present you for the last couple of slides is one project, the Adapter project, where we used those climate informations and wanted to help the agricultural sector to adapt to climate change. And what we have developed is an information toolbox, so to say, an information platform that is online, with currently 4 products for the short-term change, so for the prediction, weather prediction part, and 4 products for the climate change related part. And I'm showing this here because, I mean, unfortunately, it's only in German, because we're working here really on the regional scale. But I want to present you that as an example of what you can also do with this lot of climate data that is out there, and the process and how to do that you actually can make sense out of it, so to say. Because with this project, we didn't do that on our own. So from the very beginning, it's a knowledge transfer project. We decided to work together with key partners from the practice, and they are mentioned here. And one of those is the MPZ, and Mr. Anders, I saw he's also online today, and we have worked together. And the product I am showing here was developed in a co-creation process. And this is the calendar here, the climate calendar, because, I mean, you know it much better than me that the plant, when it's growing, it's going through different stages. And in those stages, the plant needs certain temperature and amount of precipitation. And what you can do with this climate calendar is that you can choose the plant. Here it's maize I chose, and you can then choose the stage. Now here it's just some screenshot, that's the reason why it's jumping, but you can do that online. And then you can choose the plant stages, for example, the blossom time, then a certain region you're interested in here in Germany, and the time period, like for example, end of the century, and the climate scenario, like for example, the one without climate mitigation. What can you expect? And then the results you get in this product is first a qualitative, assessment of the change, and that is seen here with those errors. So when you have a bold error, and like for example, for the temperature change, that shows you there's a robust increase in the temperature. And those errors that looking up and down, that tells you that the climate models, that the change we simulate here is not robust and it doesn't show in a certain direction. So some models say it's an increase, some models say a decrease. So with a quick view, you can see what this huge amount of climate data is telling you for those elements you selected. And you get also what you can also choose the hardcore numbers, so to say, behind those errors. You can also see that with those box plots here. Okay, with that, I would like to sum up what I've presented you today. First we looked at climate models, and they are employed to generate projections. So it's not predictions, it's projections of the future climate at multi-decadal to centennial timescales. And then we had a look what climate simulations tell us. It's the basic message is that temperature increases everywhere, but we have diverging patterns in terms of precipitation. And for the sugar beet, there we saw that in the Mediterranean region, hot days with dry soils will become the norm and rather than the exception as it is today. And even in winter, that probably the soils won't have a chance to recover. And that colder days in winter will become less frequent, so that crops that require vernalisation might be in trouble. And I presented you shortly the adapter project, the adapter platform, and the climate calendar is one of those 8 products that are already online there. And when you want to try it out, you're welcome to do that. And especially when you speak a little bit German, it would be great if you then also fill out the feedback survey we have there or get in contact with us. And with that, I also want to say thank you to the adapter team, because it's not my work I presented, but it's a whole team that behind, from GERX and also from our partners from the Forschungszentrum Hereon, the group around Klaus Gergen. So thank you very much, and I'm open for your questions.
Juliane, thank you very much for this presentation. This was, I think, for us very clear and very nice, but I suppose there are several questions around that. And I see already hands raising here in the lecture hall. Hendrik, please go ahead.
Yeah, Juliane, I'm really a nitwit when it comes to agronomy, but if we take the example of the farmer here in northern Germany, who grows barley, for example, and barley takes 110 days to go from seed to from starting the growing point in spring up to harvest. Mm-hmm. So to what extent do the farmers here have the luxury to escape part of the trouble you are painting, because the plants will start to grow earlier in the season? Right, so to what extent can they escape the higher temperatures by starting to grow in February rather than in March or April?
I mean, as I'm not a farmer myself, but just the climate modeler, I can't say do this, do that. What I would say, if you're the farmer and you have the problem, I would invite you to, we could have a look together and a closer look into the climate model data and extract the information that is then important for you. Because I mean, for example, for another type of plant, it could be a different spread that is important for you, or it isn't. So it's always, I mean, what I want to say with that is that there's not one solution fits all, but that you have to have a closer look then into the data. So from our experience from the adapter project, I have to say that when we talk to farmers, it was so that they were interested and they also approach us because, I mean, they say, okay, we experience what you also were just saying, the climate is changing. What do we have to expect? But from the experience here in the adapter project was more like that they were like, okay, this is interesting what you tell us, but it's still so far and so yeah, it's like nice. I have a look at the adapter platform, but it's nothing I can incorporate in my daily practice, as that was some feedback we get, but this is just specific for this feedback and for the farmers we work with. This might be different for others.
Yeah, okay, thank you.
Question by Rick.
Yeah, that's very informative. Thank you. I've got a question on this slide that you showed on the emission scenarios with the representative concentration pathways. So there you have the RCP 8.5. So that's, I think, a bit like worst case scenario. Some models even go sky high, you could say. So yeah, can't ignore the fact that it feels like we're doomed, right?
Yeah.
Okay. What about RCP 2.6? There you say large and sustained mitigation is required. Do you also come up with lists of recommendations? So what are you talking about there? Can you give examples?
Absolutely right. What you were saying about the RCP 8.5. This is like, yeah. This is like a crazy world when we don't do anything. Behind the RCP 2.6, I'm not sure what is exactly completely behind the scenario. I mean, like, how does every economy has to change, and what are the like climate policies that need to be implemented? But what I know, like from the recent IPCC that was published in April, is so that we see that the emissions are still rising as before, but it's still possible to turn around, but that there are a lot of efforts needed. So all the countries, what they are doing now is, I mean, that are willing to, that they are submitting their, so to say, roadmaps, how they want to come to how they want to cut the emissions. And what is newly evolving is that, and that is also what the IPCC is saying, that we won't come around to have techniques that actually extract CO2 out of the atmosphere, that we also will have to deal with that. And there are also current efforts and projects running now looking into this in more detail, like for example, planting trees, that you have more CO2 stored like in biomass, but on the other hand, like also technical solutions, like that you have chemical and physical processes to absorb the CO2. I mean, it's not answering your questions like this and that needs to be done, but it's like more assumption, and every country is doing that on their own, and yeah, and we will see if it works out.
It can be done, but how do you create the momentum that everybody's willing to sacrifice some luxury things and really stop some industries? And so painful decisions are needed, and they will not be taken, right? So
right. Yeah.
Yeah. Okay.
René, that's the question.
Yes, Juliane, thanks for this nice talk. One of the very few good things about carbon dioxide is that it promotes plant growth. So if you increase carbon dioxide, you'll just get probably more yield or a shorter growing season to get to the same yield potential. Is this effect been included in your adapter predictions, that you get also this beneficial effect of increased carbon dioxide in the atmosphere?
As we don't do yield simulations, we just look at the climate. It's not considered there, but it's like, yeah, I mean, I know, like, for example, for wheat, that it can be beneficial. But what we want to do with adapter is more like really looking at the climate side And what we see there also in the analysis of the climate projections, that the extremes will become stronger and more often and more frequent. And then it can also be like when such CO2 is beneficial for your plant and it grows better, that when you have a heavy precipitation event and in combination, I don't know, with the soil that is then flowing away, yeah, your yield is also destroyed, isn't it? So, and it's more like that when we work together with our key partners, that we look at those, or that we want to identify those extreme events, that we can also look into the data, what to expect, if that will occur more often or not.
Okay, thank you.
It's really weird talking to a screen and not seeing any people and asking the questions.
Sorry for that, but we only have that one camera that
Yeah, no, it's fine. It's just
to
the way it's
the desk up there. But we have to improve also on that. But there is another question by Ben.
So you mentioned before that one of the challenges when you talk to farmers is that it's quite a way in the future. It's almost too diffuse to act upon the information that they're receiving. So keeping that in mind, how do you think we can fill the gap? You know, maybe some of the audience here is some of the group of science which can help to fill the gap in figuring out what type of different plant growth scenarios would occur, or what type of genetics might be required. I mean, where do you see benefits or opportunities to interact from your side? Where can we work better together to try and help the end user in the end? I mean, the agriculture in the end.
Yeah, there was also an experience for us that when we designed like this adapter project, that we were thinking that we would much more, that we would much more design and deliver this project for the farmers itself. But it turned out that like plant brewing companies are more interested in that, and that we're working there a lot together. And also what we didn't have in mind before, but which also seems to be a good channel, is education. That we have like quite a lot of feedback, like from educational schools. I don't know what it is in English, like that actually do the education for farmers, and they starting now incorporating those informations there. And I think that is also a good way of kind of awareness raising, and then this taking this also to your field and taking your decisions there. That is also one channel through which this can also work.
Okay, so Eva raised her hand in the Zoom. Please go ahead.
It's hello, very nice presentation, but this comment here about elevated CO2 and also Fabio's lack of correlation with photosynthesis and growth. The question is to what extent growth is source limited. I mean, if growth is source limited, then photosynthesis will have a strong determining component in the growth. But I mean, the data that Fabio presented, and there are some other phenotyping of photosynthesis. Stephen Drever had made it on 64 wheat cultivars in the field, and he couldn't find any correlation. And the year after, they used the same cultivars, and there they found a correlation to the longevity of the flag leaf, and some correlations with photosynthesis. So one year they get the correlation, another year they don't. So the question is to what extent this focus on photosynthesis will lead anywhere under normal conditions. I mean, if you have a stress condition and photosynthesis collapses, then it will become limiting. But under these normal conditions, the question is, and also Henrik, wherever he is now, all his metadata analysis, where he shows no correlation to net assimilation rate, when it's measured per leaf area. Because if you have a plant that is like, has 15% higher photosynthesis per leaf area, but the leaf area is 30% smaller than the other plant, then the whole plant will still get less photosynthesis. So yeah, I'm just wanted to stir the pot a little bit, because I mean, I am a photosynthesis person and I measure photosynthesis all the time. But sometimes I get a little bit in doubt on how much we get out of just measuring photosynthesis for photosynthesis as a target.
Right. I think we definitely have to see it in a context between sink source. I think transport processes need to be considered. Distribution in the harvest organs or in the seeds, but actually in the ear, there is some indications that distribution across the ear with assimilates is not even, and that there might be a limitation. But between the leaf, the source, and the sink, the seed, there is the stem, there is the transport, the veins. So we have to consider that. In addition to the points that you raised, Eva, of course, the leaf area, but also the architecture of the plants within the stand and in the community are different than the individual plants. So lots of things to be considered. And perhaps what you are pointing to, and what also Juliane pointed out, is that the periods of stress conditions may increase. And then again, the question arises how to improve the plants towards this increased frequency and duration of extreme situations. So maybe we need to consider this multidimensional situation, both within the plant and in the response of the environment.
Yeah, and most photosynthesis is measured at light saturation, and you measure different capacities. And I wonder how often those capacities are even reached in nature.
Right. Well, there are indications that the adaptation or acclimation to fluctuating light intensities and the speed by which the plant can induce photosynthesis or reduce non-photochemical quenching, that this makes a difference.
Yes, because there we are going into non-optimal conditions.
Right. Mm-hmm. Exactly. And if the projections indicate that the non-optimal, at least non-optimal for the current genotypes conditions would increase, then we have some things to consider or to target towards.
Yes, but then we need to be able to expose the plants to climate stress in the phenotyping context.
Exactly. That's the phenosphere.
Yeah.
All right. Thank you. Kerstin has raised her hand. And I think we have stepped already into a general discussion, which is great, which I like.
Yeah, I would still like to come back to the climate modeling, if I may.
I also have a question.
Also on, updating on this question of Ben regarding the farmer's perspective, and maybe also this lack of future vernalisation. You may also think of crops which you still don't grow very much here and that are frost sensitive. So are there models that can tell you until which date most likely the last frost is occurring, or at which point in autumn the first frost may come? I know this is a very detailed question, but very important for such type of crops then.
No, it's not such an unusual question. I know that we get this question about the numbers of frost days and when does the first frost day occur, and when the latest one, when does the frost occur again. Unfortunately, I don't have the data in my mind, but I know that we had a look. So if you're interested, we could get in touch after this workshop, and I could provide you with this information. But I do know that we looked at it, but I don't know the answer now. I would need to look it up.
Yeah, that would be great.
Good. Then probably best when you send me an email because I can't see you and don't see your name.
Okay, I will. Thanks.
Yeah, you're welcome.
I also have a question to the various scenarios. The RCP 2.5, I think was the most optimistic one, and the RCP 8.5 the most pessimistic one. The ones in between, maybe the 4.5 or 6.0, would those result in kind of intermediate linear gradual effects, as you pointed out? So a little bit higher temperatures, a little more precipitation in the northern and a little less, or is it qualitatively different, the projections that you achieve with the 4.5 or the 6.0?
I mean, it's kind of both what you were saying. It's like with the changes they simulate, they are kind of in between in this bandwidth, but it's not linear. It's not like that you can say, okay, so much amount more of greenhouse gases in the atmosphere, and then we get a temperature increase of 2 degrees or so. It's not like that because it's a non-linear process, the climate itself, and also how it's simulated in climate models. And especially when we come to precipitation, the patterns may also look a bit different. It's more for the illustration point of view that the climate modelers focus most often on the very two ends, on the very optimistic scenario and the worst case. So because with that you cover more or less like the lower and the higher bandwidth.
Right, right.
And so also from the CORDEX initiative, so really from the regional climate modelers that set up the simulations, is so that you also get more simulations for the lower and the higher emission scenario. And from there, you can also derive the more robust results so that there's less amount of resources going into the middle ones.
Okay. There's another question by Mark.
Hi, Juliane. I was just wondering, so in biology, everything reaches an equilibrium someday. So with your projection of your worst case scenario, what would be this equilibrium in temperature if you would play this scenario through? So would it reach an equilibrium, or would we heat up the atmosphere until we burn to death?
That's a good question. And I'm laughing because I don't know. I haven't seen any plots. And I think the reason for that is because of the high computational costs, because I know when there is also internal, we have one regional climate model we are running, and we have to apply for the resources on the computer before we do the simulations. And there you think about it very well, I mean, how you set up your experiment. And I think that is also one of the reasons why there are no simulations I'm aware of that go into the final end. I do know there are some simulations that are running more than end of the century, just to see what happens then. And as the scenarios, not the 8.5, but the other ones, I mean, they assume that at one point in time, there will be a reduction in the emissions. And it's so what we know from those simulations is that even when the emissions go down, that you will still have a temperature increase, and then it takes quite some time until it stabilizes because of this greenhouse gas effect of the greenhouse gas emissions, as they have such a long lifetime, even in the atmosphere, although there are no emissions anymore. So for the 8.5, when you blow more and more emissions, I have no idea. I would expect the temperature would increase, but probably there are some physical effects that at some point it need to stabilize. I mean, that's just, I mean, I don't know, it's just because I would also assume that as a nature, everything goes into kind of equilibrium at some point.
Exactly, because I mean, I had the pleasure to listen to some astronomy lectures in university, and so you see like these absorption bands from the spectrum, and carbon dioxide is quite a very narrow band. So there must be an upper energy absorption limit reached someday, somewhere. So I'm just curious, where do we reach that?
Yeah, but I think nobody wants to try it out in real, so I don't know.
Not in a live experiment, but a simulation would be enough.
Would be great. Probably there are some simulations around, but I'm just not aware of it. And it's not like in the initiatives that all the climate modelers have that in their in their normal simulation metrics as one of the experiments or everybody's doing. But I'm sure that one of the other climate modeler already had this question and was running a simulation like that to find it out.
Likely. Okay. Thank you anyhow.
All right. I have one more question to you, Juliane, about the regional dimension of your models or your projections. So can I go into your resource or website and ask for projections for the Landkreis Harz or the Salzlandkreis, or even smaller, the fields of IPK here in Gatersleben? Or is it rather on the states level, or yeah, where's
the limit?
Sorry?
Where's the limit? I was saying it's that quite often we actually get those questions for the Landkreise, and it's as we get it so often, we have developed a tool. It's called Klimaausblick Landkreise, and when you go to our website, you get this information for the Landkreise, and I'm just posting it here in the chat. So when you go there, you can select one of the Landkreise, and then you get the information about the precipitation and the temperature for what I basically showed you for Europe for your Landkreis. So this is possible. When you need to have it on a smaller scale, then it gets, like on a higher resolution, it's tricky. Because from there it's not like the standard output of the simulations, and then you would need to. It depends from case to case. But it's like that we say this is like the resolution of a few kilometers. That is like the standard now. The regional climate model, what is provided as an output. When you go on a higher resolution, there it becomes tricky. There are some methods how to do that, to apply some methods that you can extract also information, but it's not like we are not there yet, so to say, with the regional climate models to provide like standard output for a scale that is less than a few kilometers.
All right, I think that's fair enough and amazing enough that it's possible already at that level to.
Yeah, we're also amazed by that. I'm very happy about it. We launched it end of last year, and there's a huge response to it. So this information is actually really needed, and not only from the scientific community, but also from administration and all different decision makers.
All right, excellent. Thank you very much once more.